Okay, so for my describe sheet, I decided to discuss full adders. So starting off with the definition, a full adder is a digital combinational circuit that is adding three 1-bit binary numbers A, B, and carry input and produces two outputs, the sum and carry out. And it's simply what it means is that the carry in and carry out is carry in bits are carrying in bits essentially from a previous adder. And you're getting a range from 0 to 3, but you're representing this in a binary form. So for example, the number 2, so when you're adding 1 and 1 together, you're going to get 2 as a sum, but you're going to write it as 10 or 1, 0, which represents the binary form, and I'll show that later on. And then carry out is essentially going to be the same thing. So for this drawing, it's going to show the logical circuit of a full adder. So you're using two extended OR gates, A and B, as well as CN. Are using A and B for the first extended OR gate, and then A, B, and CN for the second extended OR gate to get the final sum S. And then for carry out, it's implemented using extended OR and OR gates. So for the first hand gate, you're using A and B, and then the second is going to take extended OR A and B, CN, and then you're going to then combine that as ands, and then combine what you get from here into the carry out gate, which is summarizing those outputs that you got previously. And then down here is going to be the truth table for the three inputs A, B, and CN, and the two outputs on the sum and carry out. So you can see that over here. And then to the side is simply an example of just what carrying over means. So you're going to be adding, so 0 plus 0 you get 0, 0 plus 1 you get 1, but here you get 1 plus 1 is technically 2, but to represent that in binary form, we write that as 0, and then you're carrying over 1, so you got that 1 being your carryover number. And full adders are significant to engineering, specifically to arithmetic and logic units, which are ALUs. So how they work is that full adders are those the building blocks of the ALUs and microprocessors and microcontrollers. So they perform binary addition with extra logic, subtraction, comparison. So for example, a 32-bit CPU ALU is going to use a chain of full adders to perform 32-bit addition in one cycle. And moving on to why this is significant in the real world, full adders are foundation of computation. So every single modern computer, smartphone, or any embedded system is going to rely on binary arithmetic. These large adders, so when we think about our computers being 4-bit, 8-bit, 32-bit, are basically built by chaining those adders together, and that's how you're creating that space. And a connection to other engineering learning, this is just a kind of an interesting way to kind of think of an engineering parallel, is that adders are building blocks. You're adding multiple chains of adders together. And you can think about this in mechanical design, where gears and levels our levers are used, are modular units that combine to form the machines. And the same goes for beams and trusses to form bridges. You're taking complex parts and essentially simplifying it to get a more standardized modular unit. And that is it for full ladders.